let's get started. I'm pleased to introduce today's speaker, Dave Ferguson from Intel Research. Let me tell you a little bit about Dave. He received his PhD in robotics from Carnegie Mellon in 2006. 2 years ago.
Yeah.
While Dave was at CMU, worked on a number of things, including the Robotics Collaborative Technology Alliance, where he developed quite a few planning algorithms, also the mind mapping project, and last but not least, Dave developed software that is running on the Mars rovers, Spirit and Opportunity. When he graduated, he joined Intel as a research scientist. He also joined the Tartan racing team as the planning lead, and we all know what happened there. Of course, Tartan racing won the race. And today, he's going to tell us all about that. So the title of his talk is Motion Planning in Urban Environments. Dave?
Thanks very much, Tony. Just in case any of you are not already yet on the autonomous vehicles bandwagon, I'd like to start by giving a few reasons why I think you should be. So firstly, in the US, there are tens of thousands of driving-related fatalities every year, and roughly 95% of these are caused by human error. So having autonomous vehicles that could reliably navigate through streets without ever getting dozy or daydreaming could prevent a huge proportion of these accidents and the damage they cause. Secondly, these vehicles could also provide independence to people that are currently unable to drive due to age or ability, and they will revolutionize the industry and public services and transportation and public services industries. But these sample examples are really just the tip of the iceberg, because not only will these vehicles drive us around, but they will perform all of the errands that drive us crazy in day-to-day life. So they'll go pick up our dry cleaning, they'll do our shopping for us, they'll take our kids or our grandparents to soccer practice, you name it. And in the future, we won't need to have garages to store our vehicles. We won't ever need to find parking spots. You know, we realistically may not even need to know where we live, because our vehicles will take care of all of this for us. And perhaps most importantly, we're going to be able to use them to fight crime like David Hasselhoff. So I think you'll agree that the potential really is pretty exciting. Now, unfortunately, you can't go out and buy one just yet. Tony Tether tried, and this is what resulted, the Urban Challenge last year. And thanks to the Urban Challenge, I think we're a great deal closer to this realization than we were previously. Now, in the Urban Challenge, the task was to have an autonomous vehicle navigate through an urban environment and perform a series of navigation missions. The overall distance was on the order of 60 miles, and the time limit was 6 hours. Now, the fastest vehicle won, but you had to abide by rules of the road and speed limits and basically normal driving criteria. And it took place in November last year. Now, going into the Urban Challenge, there already existed a strong body of research on vehicles traveling at high speeds on road-like environments from the first grand challenges. Now, these vehicles proved that they were well capable of handling the speeds that were required for urban driving. But they weren't required to have to deal with interactions with other vehicles, road rules, or complex maneuvering. Now, we also had impressive lane following systems, such as the NavLab family of vehicles developed here at CMU, that showed that we could drive in lanes, stay in our lane for thousands of miles at a time on highways. But as impressive as all of these combined systems have been, they were still a far cry from being able to cope with all the general challenges of urban driving. And the reason for this is because it's a really tough problem. So in the Urban Challenge, we didn't have to deal with pedestrians, we didn't have to recognize street signs or traffic lights. But even without these challenges, there are already plenty of things for us to keep busy on. So successful vehicles were going to have to detect and reason about other vehicles traveling at high speeds, long distances away. We were going to have to avoid static as well as dynamic obstacles, do all of the intersection precedents and all of the sort of road rule logic that we need to do every day when we're driving. And we had to perform complex maneuvering to maneuver into parking spots. Now, in particular, for the motion planning side of things, the Urban Challenge presented a number of new big problems that we had to solve, and perhaps the most significant was these very complex parking maneuvers in very large areas, and I'll talk about that a little bit later. Okay, so I hope you've all had a chance to meet Boss in the flesh, and if you haven't, you know, perhaps shame on you. But in case you haven't, he's a 2007 Chevy Tahoe. He has over 25 sensors and 10 incredible Intel Core 2 Duo processors. Now, his software system consists of 4 main components. We have perception, mission planning, the behavioral executive, and motion planning. And the way that information flows through this system is that perception first processes it to figure out where boss is, where the road is, and then where all the other vehicles and static obstacles are in the environment. It then feeds this information to the planning components and to the behavioral executive. And mission planning then computes the fastest route through the entire road network to get to the current checkpoint. And it does this for every position in the world. And it feeds this information to the behavioral executive, which then combines this sort of high-level route information with local traffic and obstacle conditions. And it then pumps out a motion goal to give to the motion planner, such as drive down this lane to the next stop line. Now, the motion planning component then tries to generate a trajectory and execute this trajectory for the vehicle to get towards this motion goal. So this talk is focusing on how we develop the motion planning system shown here in this part of the architecture. Now, some of the stuff that I'm going to show will be very familiar to most of you, to many of you, because some of it is existing work from the first grand challenges that we used and pulled in because it was solid. Some of the rest of it are brand new algorithms that we had to develop to try to cope with the new challenges. Now, my goal, my hope is that you'll leave here with a good sense of how all these pieces fit together, along with some of the tricks that we came up with along the way. But before I get stuck in, I'd like to highlight the key contributors, which were an amazing group of people that did ridiculous things to make all of this happen. So in particular, Max Likachev, Tom Howard, and Sasha Kolsky spent many, many hours behind whiteboards and in misbehaving vehicles trying to get the motion planning system right. And the related vehicle controls team of Hong, Tug, Jared, and Mike fine-tuned our Tahoe so that we had fantastic performance at both high speeds and when performing very complex, precise maneuvers. Now, those of you who were at Chris Urmson's talk a few months ago might recall a story that he told of how aggressive Boss was during testing. And it was these guys, these planning and controls guys, that pushed the vehicle to try to keep 2 wheels up and 2 wheels down at pretty much all times. So I think it was taking corners hot was the exact expression that Chris used. And that was very important to us. Okay, so in our software architecture, the behavioral executive is feeding these motion goals down to the motion planning system. Now, these goals fall into 2 broad contexts. There are on-road goals, which are, say, follow this lane, this desired lane, and take me to the next stop line at the end of that lane. And then there are unstructured planning goals, such as I want you to reach this particular pose or parking spot in a parking lot. Now, the motion planner then attempts to get the vehicle to reach those goals while accounting for environmental constraints, such as where the current lane is, where the parking lot is, static and dynamic obstacles, speed limits, etc. Now, the basic framework of the motion planning system is the same regardless of which context we're operating in. So we first start by generating a path that's going to take us to the goal. We then generate a set of trajectories, sort of local actions, that will track this path. We then evaluate each of these local actions and we select the best. And this evaluation stage takes into account environmental conditions, speed limits, how smooth the trajectories are, and so on. Now, as I mentioned on the previous slides, there are 2 main motion planning contexts. There's the on-road planning and the unstructured planning. And the rest of this talk is split up into 2 parts describing how we do each of these different contexts. Now, I'm going to go through the path generation, trajectory generation, and evaluation stages of our on-road planning framework pretty quickly, as this is probably more familiar to many of you and is fairly similar to some of the successful approaches in the first grand challenges. But I will mention some of the new capabilities that were required for our urban driving. Okay, so when driving on roads, the goal is typically to travel down some desired lane. So we begin by taking our representation of the road, shown here in blue, and we extract the center line of our desired lane. So this is shown here in red. Now, this represents the nominal path that we'd like the center of our vehicle to take, assuming that there are no obstacles or any other vehicles misbehaving. To then track this path, we generate a set of trajectories that all attempt to track the path while allowing for some maneuverability to account for obstacles. So to do this, we select some endpoints that are all at a fixed distance down the path, but they vary in cross-track offset from the center of the path. And to each of these desired endpoints, we generate two trajectories. So we generate a smooth trajectory and a sharp trajectory. And the smooth trajectory, funnily enough, attempts to smoothly transition the vehicle from its current state to the desired state. The sharp trajectory, on the other hand, involves an initial sharp jerk of the steering wheel, and the point there is to be able to abruptly react to suddenly appearing obstacles that really require some evasive action. Now, I'd like to briefly go through how we create each of these trajectories, because it involves a pretty cool trajectory generator algorithm developed by Tom Howard and Al Kelly here. So the task of the trajectory generator is to compute a parameterized set of controls that will take the vehicle from its current state to some desired local end state. So one of these endpoints that we're trying to get to along our path. So the basic idea is to first grab an initial set of controls parameters and forward simulate using this set of controls and a very accurate vehicle model, and then figure out where the vehicle would end up if it applied these controls. Now we then compare where we ended up with where we'd like to end up, and we use this error to update the parameters that were in our controls so that we can reduce the error. And we then continue these last three steps over and over again, and we get gradually closer and closer to where we want to be until we're within some desired error bound. Now, because this optimization can be expensive, it's important to start with good, close initial guesses for the controls parameters. And to do this, we create offline a lookup table, a 5-dimensional lookup table that stores for all ranges of initial velocities and curvatures the set of all reachable x, y, and theta positions that we can get to relative to that state. So in blue here in all of these images, you're seeing the set of all possible x, y headings that you can reach given any initial velocity and curvature value. So all of the ones that we can reach for all of the initial velocity and curvature values. And in green, you're seeing the specific places that we can reach for a given initial velocity and curvature pair. So here we have a velocity of 5 meters per second, an initial curvature of 0. So this is the steering wheel pointed straight forward. And you can see the green reachable states are symmetric about this horizontal line. In the second case, we have the steering wheel cocked all the way to the right. And you can see it's very heavily skewed to the right, the states that are reachable, and likewise in this one to the left. And we then store both the states that are reachable and the associated controls parameters in our big lookup table to be used online. And then when we're trying to generate a trajectory to a desired endpoint online, we first look up in our lookup table the closest states to the desired state, and we grab the controls parameters associated with those trajectories, and we interpolate between them to get a good initial guess for the parameters that we want to reach our new state. So here in this example we have in green, and I hope you can see this in the back, in green we have the position and heading of the desired endpoint that we're trying to reach. And in red we have the 4 closest states in our lookup table to this desired state. And so what we do is we grab the controls parameters that are associated with these 4 red trajectories, and we interpolate between them, and we come up with this resulting blue trajectory here. And you can see this does a pretty good job of approximately getting to where we're trying to go. So we then use this as our initial guess, and we perform the optimization routine that I mentioned on a couple slides earlier. So we take the endpoint where we ended up at the end of this trajectory, and we compare that to where we're trying to get, and we use that endpoint error to update our parameters so that we get closer. And you can see here after 3 updates, we're able to get this green trajectory, which pretty much nails the endpoint that we're trying to reach. And so that's the trajectory that we return. So we've successfully generated our set of candidate trajectories, and we then evaluate each of these to figure out which one we actually want to execute. So the first stage is we look at how closely they track the path, so whether they end up on the path that we're trying to reach and what the maximum cross-track error is, particularly whether they have the vehicle go out of its lane. But we also take into account static obstacles. So in red here are some obstacles that have been observed in the environment, and in blue are curb points. So these are sort of lesser geometric features that we can hit, but we don't really want to hit. And so we take all of these into account, and we score each of these trajectories. Now we then also reason about other dynamic obstacles that we may have observed. So here in green is another vehicle that perception has seen coming in the oncoming lane. and we predict where we think that that vehicle is going to go based on its current position, its heading, its velocity, and where it is relative to the lane, so the offset that it has relative to the lane. And we then compare its predicted trajectory through time with each of our candidate trajectories through time to see if there's going to be any overlap, how close we get, and etc. So we evaluate each of these trajectories, and then we select the best one according to all these evaluation criteria, and we then execute this. So here in blue is the best trajectory which we've selected to execute. We then repeat this at 10 Hertz. So here is the close call example that I just showed from the Urban Challenge, where we got perhaps a little bit closer to Oshkosh than we would have liked. Now this was definitely the one vehicle in the competition that you didn't want Boss going up and giving a great big bear hug to during the race. So that clip we saw afterwards, and I think we were all glad that we saw it afterwards. So this on-road planning framework that I've just described is basically what was required in the first couple Grand Challenges, except that we've allowed the addition of dynamic obstacles so we can handle other vehicles, and we have a pretty snazzy local planner involving the trajectory generator. So there are also some additional demands in the Urban Challenge, things that we had to do, such as lane changes. So our framework actually allowed lane changes to be performed pretty easily. We figure out when we want to change into another lane, we simply extract our path in the center of that lane rather than the center of our current lane, and then our generation of trajectories will naturally transition the vehicle into that lane smoothly. So here's an example from the race where we passed, this is a 2-lane, same direction road. We passed a slow-moving traffic vehicle. You know, the human drivers were really wimps in the Urban Challenge. We passed a slow-moving traffic vehicle, jumped into its lane, and just continued on. And this next slide shows, this is the passing of a chase vehicle that actually stopped in the road. So this was a chase vehicle for a robot that I believe, I don't think this is even it, I think it was a little bit further up. But it stopped, Boss came up behind it, it also stopped, waited patiently for about 15 seconds and then said, okay, if you're not going, I will. Circumvented the vehicle and then got back into its lane. So here it's actually in the oncoming traffic lane, so it knows that it needs to get back into its lane very quickly. This was not actually a solid yellow line in our representation, so DARPA said that we could swap out of that lane if we had to. Okay, now U-turns were a new task that required a little bit more work. So to perform these, we had templates for performing full U-turns and K-turns, and depending on how wide the road was, we selected between these templates and updated their parameters so that Boss, wouldn't stick itself out of the actual road. So in this example here, this is from one of the qualification runs we had. Boss had actually traveled through this road once already, and then DARPA paused it, put a whole lot of obstacles down, and then we had to detect that there were these barrels, that the road was blocked, perform a U-turn or a K-turn in this case, and then reroute to get to where we're trying to go. So in this case, we extract one of these K-turn paths, we track it similarly to how we track our normal lane paths, and then once we're back in our lane, we sort of take off again like a bat out of hell. Now perhaps the scariest, or definitely the scariest capability that Boss had to have was defensive driving in on-road scenarios. So DARPA actually specified that we had to be able to detect another vehicle in our lane coming towards us, reason that there was going to be a collision, and leap off the road to avoid that collision and let it pass. So to do this, what we did was, once we detected that there was a vehicle coming towards us and that a collision was inevitable, we created a virtual lane that stuck off the right side of the road and was parallel to our current lane. We then generated our trajectories into this virtual lane, slowed down significantly, got off the road, waited for the rogue vehicle to pass, and then got back onto our road, onto our desired lane, and continued. Now, this was pretty frightening behavior because, if you have any inaccuracy in detecting where the vehicles are or where you are, then you're going to end up jumping curbs and doing all sorts of things that you don't want to do. Yes?
Suppose you're passing a car, so you're in the oncoming lane, and then you see a car coming toward you that you didn't expect to see there. Do you go over further left under the shoulder, or do you expect him to do that?
We don't. So we actually debated this. So the same thing sort of arises if you're in a one-way road. We never consider going left because I think the end result of all of our debates was if we go left and they go right like they're supposed to, then we're going to crash into them. So we would stop in that case, or we may try to get back into our correct lane, but we won't ever jump left. Okay, so that concludes the on-road planning portion of the discussion. So let's move on to the unstructured parking lots. Now the challenge in unstructured environments is actually generating the path that the vehicle is going to track. So in on-road planning, this was basically given to us for free because we knew which lane we wanted to be in, so we knew that basically the center line of that lane was the path that we wanted to track. But in parking lots or unstructured areas, we don't have this path, and generating it can be pretty difficult. So imagine, we're in a very congested parking lot and we're trying to navigate into a tight spot. Then the path that we end up taking may involve all sorts of complex maneuvers to squeeze between obstacles and get to where we want to go. We can't just compute a straight line path to our desired goal because we'd easily get stuck. So this was definitely the most challenging motion planning scenario, as it involved planning over very large distances. So DARPA specified that we should be able to handle parking lots that were up to 200 by 200 meters in size. So that's 8 football fields and a pretty frighteningly large space. It also involved dealing with static and dynamic obstacles, and importantly, in these open areas, these dynamic obstacles could be moving along basically arbitrary trajectories through the space. We don't have a good idea of what their behavior is going to be, particularly if they're, stupid robots. It's also relatively high speed, so 15 miles per hour or so was the speed that we were trying to hit in parking lots. And it also involves very complex maneuvers with a huge non-holonomic vehicle. If you've seen Boss, he's something like 5.5 by 2.3 meters in size, so he's a big boy. Now this sort of planning was also required, not just in parking lots, but in on-road planning scenarios when Boss got stuck. So for instance, if our lane was blocked or our intersection was blocked, or we were just confused for whatever reason, we would invoke this sort of unstructured planner to try to get us out and get us back on track. Okay, so I'll focus in this part on basically how we came up with this path to track, the search space and the search algorithm that we used, as well as some optimizations, and then I'll talk very briefly about how we then track the resulting path that we come up with. Now we knew that in the worst case we were going to have a really powerful planner to perform these very complex maneuvers. So we developed a lattice planner that reasons over a 4-dimensional search space, so the position of the vehicle, the heading of the vehicle, and the current velocity of the vehicle. Now just to be clear, a lattice is a graph, so it consists of a set of nodes that are connected to each other via edges, but the special thing about a lattice is that each of these edges represents a continuous trajectory action that can be taken from one state to the next. So for each state we consider a fixed set of such actions, and I'll get rid of the Boss model here so that you can see the actions for one particular state in the center here. Now each of these actions is, as I said, a continuous trajectory, and we use the trajectory generator to snap the endpoints of each of these actions to one of the states in our discretized state space so that we have this perfect connectivity between the nodes. Okay, so we've set up this 4D search space and we have actions from every state in this space. So now all we really need to do is start from the initial state where the vehicle is and search for an optimal path through this search space to get to the desired goal state. Done. Now unfortunately that's actually pretty tough because we're dealing with tens of millions of states and billions of actions, and each one of these actions requires an expensive convolution to figure out what its cost is, particularly since we have this huge non-holonomic vehicle that we're sort of carrying around with us like a lot of weight. And we also need to be able to replan whenever we get new information or something changes in the environment or another vehicle does something unexpected, which in practice is all the time. And we have to do this really fast because Stanford's trying to steal our parking spot. But this state and action space is so large that planning good solutions through it is going to require that Boss sits around and spends most of his time sitting there and thinking rather than actually moving. So we have to make this more efficient. And the first way that we do this is to use a multi-resolution lattice. So in the vicinity of the robot and the goal, where very complex maneuvering may be required to get into or out of tight spots, we use the high-resolution state and action space that I showed on the previous slide. So here we have 36 actions from each state, and we have a heading discretization of 32. So we're reasoning about 32 different headings. And in other areas where we're further from the robot or the goal, we use a lower resolution action and state space. So here we have only 24 actions, but more importantly, half the discretization of headings. So our state space is much, much smaller. Now, to produce smooth actions, though, we need to make sure that our high-res and our low-res elements or areas of the state space intersect smoothly. And the way that we do this is that we make our low-resolution space to be a subset of what the high-resolution one is, so that every action that's in our low-resolution action space is also in our high-resolution action space. And we then just restrict the actions available from each low-resolution state to be only those actions that will end up on other low-resolution action states. Sorry. Now, this turns out to be a pretty powerful idea. The multi-resolution nature of the search space is transparent to the planner. It enables us to significantly reduce the number of states and the number of actions, the branching factor that we have to deal with, and we have nice, smooth solutions. And in fact, we can prove bounds on the quality of the resulting solutions relative to our low-resolution action space, which is nice. Now, what's more, the implementation is really very straightforward. When we're performing our search and we expand a node, we simply check what the distance is from that node to our goal or start. And if it's close, we use the high-resolution, dense action and search space. And if it's far, then we use the low-resolution one. So it really was quite an easy thing to do. And the results are pretty striking. So in this small example where we're planning between one parking spot, and these parking spots encode an orientation. So we're planning from this one to this one, and this is the edge of our parking lot that extends out of the image. We had a factor of 3 improvement in time using the multi-resolution approach as opposed to the high-resolution one. And this improvement increases the larger the distances are that we're dealing with, because a larger proportion of our state space is going to be the low resolution. But even with this multi-resolution lattice search space, we still can't generate optimal solutions to very hard problems fast enough. So the boss is still going to have to sit there and think a little bit when he's confronted with a very hard problem. So to make sure that we always have a solution as soon as we need one, we use the anytime Dstar algorithm to search through this lattice. Now, the anytime component of this algorithm allows it to very quickly generate an initial suboptimal solution with a guaranteed suboptimality bound, and then it can improve this solution while there's still time available. So the vehicle can grab the best solution that it has currently, start to execute this, and then while it's executing it, it can be improving it, and it can then grab the next best one straight off the pile. And each of these solutions is reusing information from the previous solution so that they're able to do it very, very fast. In fact, we've shown that the overhead associated with running these multiple solutions is very, very small compared to what it would take to just generate the best solution generated so far. So we're pretty fond of this fella. Now, this graph here shows the solution improving over time for the sample search problem that we showed in the previous slide. So here you can see that an initial solution is generated in about 100 milliseconds, and that's this solution here. It has a suboptimality bound of 3, which means that it's at most 3 times as expensive as the optimal solution. But over time, you'll see these discrete jumps, and these are when the solution jumps in quality. And here, after 600 milliseconds, it's converged to the optimal solution. So what's nice is that if we decide, we need to start going right now, we can start executing this solution, and as we go, we can actually improve it, and it will converge to the optimal while we're executing it. Now, the second advantage of Anytime Dstar is its Dstar replanning capability. So this enables it to very efficiently update its best solution, so the best one that it's generated so far, when new information is received or the environment changes. So here we have a very narrow parking lot that Bob crafted up for us in Arizona. It was really more of a walkway, we like to joke, where Boss is trying to plan from this parking spot to this one over here. And again, the orientation is encoded. So it's that he's planning from this orientation and he has to get back to the same orientation. And this is the initial solution that he generates. Then when we provide him with this obstacle information, he's able to update this solution efficiently to generate this updated plan that has him do a little bit more maneuvering and then actually back into the spot in the end. Now, like any heuristic search algorithm, Anytime Dstar relies on a good search heuristic to be most effective. Now this heuristic needs to estimate the cost of a path between any two states in the search. So for instance, a state that we're currently expanding during the search and the current goal of the search. Now traditionally there are various classes of heuristic algorithms that exist. One popular kind are what I call mechanism constrained heuristics, which try to take into account all of the constraints of the vehicle and use as the heuristic an optimal path assuming that the environment is empty. So here if we have boss trying to get from this position to this desired pose pointing this way, in bold may be the optimal path that he could take assuming that there are no obstacles in the environment. Now the very nice thing about these sorts of heuristics is that we can pre-compute all of them and store them in a big dirty lookup table and then just grab from that lookup table when we're online trying to generate it. And here you can see that this is much better than doing a simple sort of straight line distance because that straight line distance is not going to take into account the significant reorientation that's required to get to the goal heading. Now, second class of heuristics are environment constraint heuristics. So these ones take into account some of the information that we have about obstacles in the environment. And typically they work by solving a simplified search problem. So in our case, we may try to solve a 2D search problem with a holonomic approximation of our vehicle instead of the full 4D non-holonomic search problem. So here if we have this big obstacle in our environment and we're trying to generate the heuristic path from this state to this state, you know, by using a 2D environment constraint heuristic we would plan around this obstacle, whereas a mechanism constraint or a simple straight line path would have us go straight through it. So both of these heuristic techniques have weaknesses, but interestingly they have advantages that are complementary to one another. So we thought that we'd combine them, and we do this by using as our heuristic the maximum of the environmental constraint heuristic and the mechanism constrained one. And this turns out to work really well. We thought that it was a good idea, but we didn't realize just how good an idea it was until we started looking at some of the numbers. In fact, some of these numbers we generated after the Urban Challenge, and you know, we were kind of surprised. But it can result in a search. So this is the time for the overall search. So the final effect of what the heuristic does. And you can see here that our combined heuristic is more than 20 times more efficient than the most efficient of the two heuristics that we're actually combining. So this was pretty nice. And this is not really a very nasty scenario. I mean, this is the same parking task that we had before, but just a wall of obstacles, which you could think of as being a curb island, very possibly in the parking lot. Now, as well as these, we employed a number of other optimizations to make everything as quick as possible. Now, most of these I'm not going to go into in detail, but we used inner and outer configuration space maps to reduce the number of expensive convolutions that we had to do for each action. We also pre-computed the relevant cells for each convolution so that when we had to do them, we could do them efficiently. We also used an efficient hierarchical representation to figure out very quickly which actions are affected when new information is received, which really has a big effect on the replanning speed. And we incorporate constraints on the motion of the vehicle based on its current context. So in parking lots, we constrain it to stay within the lot, and we can actually encode prior information in the form of sort of aerial imagery that we could process to extract features like curbs and encode that in these initial cost maps that we give the planner. Now, two areas that we focused on that were really big wins for us were pre-planning and running multiple planners at the same time. So for pre-planning, when we were coming up to a parking lot and we knew that we were going to be generating a plan from the entrance of that parking lot to a specific parking spot, we would boot up our planner before we got anywhere near the parking lot, so that by the time we entered into it, we already had a beautiful plan waiting for us and we didn't need to stop and wait. And in a similar fashion, when we were planning and navigating to our first parking spot, we would start up another planner that was planning from that parking spot to the next place that we wanted to get to, so that as soon as we reached our first one, we could then just look up, load in that new plan, and we wouldn't have to pause to wait for thinking. And this was nice because with two of these, we could sort of leapfrog them and do this indefinitely from parking spot to parking spot. Now finally, to avoid other vehicles, we updated our cost map with high-cost regions based on where the vehicles were so that we would give them a wide berth. So here we have very high-cost regions close to the to the other vehicle and slightly lower cost regions a little further away, so that we're going to try to stay well clear of them if possible, but we will allow ourselves to get quite close if we have to. Now, the other nice thing about having this sort of general cost map representation is that we could offset these costs to the left of the other vehicle, so that we would naturally get human-like right-hand rule behavior when we're in unstructured environments. So we would naturally prefer moving to the right, which we found to be quite useful in parking lots. Okay. So once we've generated these complex lattice paths, we then track them in a similar way to our on-road paths. And the one exception here is that all of the trajectories that we generate to track the path attempt to end back on the path itself. So each trajectory is in fact a concatenation of two, with the first coming out a little bit from the path, similar to our on-road trajectories, and then the second starting from where that one finished and trying to come back to the path. And we did this because we wanted to reduce the risk that the vehicle gets off the path and finds itself in a location that is very difficult to maneuver out of. You know, we've spent a lot of time and effort going into generating these nice paths, so we don't really want to throw that away by having the vehicle just ignore them and drive off. Now, our test team, and I'm really glad to see Bob here today, he's to blame for a lot of this, really put this planner through its paces. They did a fantastic job of really testing the heck out of it. So here, this is a parking lot that was set up in Pittsburgh, one of the more devious ones, where there are a whole bunch of cones that the vehicle had to get through, and then it had to jump from spot to spot. So here we have, this is a wall that was set up that it was going to have to squeeze through another sort of wooden box, car-like shaped next to our parking spot. So here Boss is just entering into the parking lot and he's trying to get to a goal that's over here. This was back in July, so we didn't have pre-planning, we didn't have our multiple planners. There were a lot of optimizations that we didn't have going. But you can see he had to swing around all of these cones initially to get to where he's trying to go. And this is sort of the sort of example that we love to see, because this is the kind of environment that you would fail hopelessly in unless you had a sort of very hardcore planner, which we did. And so here it's then going to squeeze through this little gap between these panels, and then it's going to come out wide to slot in nicely to the first parking spot. Now it then jumps between a whole bunch of different spots, but I'll just show you this first one to give you an idea. And here's an example from simulation where we could create the biggest parking lots that we could possibly imagine. So this is a 200 meter by 200 meter parking lot. Unfortunately, we didn't have one of these in our test site. You know, we should have been doing stuff at Walmart, I guess. I don't know where else you find such large parking lots, but DARPA apparently thought it was important. And here we have it Boss is trying to get to the exit here, and we're throwing down obstacles shown in white as he's driving along. So we're making it pretty tough for him, but he just keeps nutting away, and eventually he does get out. I'll just let this play a little bit longer because you'll see we're particularly mean to it down at this corner. But we were really testing this out in simulation. So this is running on the vehicle hardware, all of the computers that were on the vehicle, so that we had a good idea of how long it would take if we were going to be set up in a huge parking lot. So you can see here, then we just go and block it off, and you can almost see him shed a tear. But he pretty quickly loops a new path around. He didn't need to stop. So another important factor here is that if he's traveling at 15 miles per hour, then if there's any lag whatsoever in our planning, we really need to make sure that we're planning from a point far ahead on the path. So there was a couple seconds lag when we closed this area off. For the plan to update, but you can see he didn't need to stop because when it updated from a position that was further down his path. So trust me, we eventually let him get out of the parking lot. And this is an example from one of the qualification runs. So here you can see there's a path that is already there. This is in green is the parking lot. There's a path already there by the time Boss enters it. And this was great. We were really excited about this because DARPA set up all of these cars. They had a big wall of obstacles in the middle. And here, interestingly here, as he's coming in to get to the parking spot, he observes more of this obstacle on the left, this car, and he realizes that he's not going to be able to continue along his current trajectory. So he has to replan. Now at that point, he could stop, back up, reorient his wheels, and then go in straight, but he decides that it's faster, according to his cost function, to just swing around in one sort of smooth action and slot into the parking lot. So you can also see here that before he's even in this parking spot, there's already this plan generated for him to get out of the spot and then get out of the parking lot. So here he immediately starts executing this plan, pulls out, and then drives out of the lot. You might see him pause for a little bit here. He was kicking up a little bit of dust that hadn't ever been a problem for us in Pittsburgh or Arizona or California, but it turned out that the dust that they had at the Urban Challenge was particularly evil. So you'll also see a little bit of it as he approaches the end, at the exit of the parking lot. There'll be a little bit that comes up, just some red, little red cloud for a while. Somewhere around here, I think, and maybe I missed it. But he makes it out of the parking spot and continues on. And then this final video is from the race itself. So in the race, there were 3 parking lots, and we were really excited when we first saw these because there are all sorts of spots opposite each other, and we thought, you know, DARPA could really make this interesting if they put a whole lot of parked cars and a whole lot of other vehicles in the way to make it challenging. In the end, it was a completely open parking lot. But the fact that this parking spot was 180 degrees away from us, the one that we had to reach, meant the boss could still sort of show off a little bit and do his little dance getting in. But you'll notice that as soon as he hits this one, he starts off again. There's no lag for him to wait to have to plan a new path out of the spot. Okay, so at the end of the day, boss completed the full 60 miles of the challenge. I guess, you know, Tony already gave away the ending. But our error recovery framework was given a really good workout with 17 different instances where we got stuck. Some anomalous situation happened during our on-road driving, and we had to invoke the Lattice Planner to get us out of it. And there was a single bug that caused us to mistakenly take a U-turn and drive an extra 1.6 miles to get back to where we were trying to get. Now, this bug was that the local planner wasn't refreshing its moving obstacle set in certain error recovery scenarios. So there was a vehicle where it was trying to get initially. That vehicle moved on and was long gone, and it still thought that it was there. So it was just as well that we had this very nice error recovery framework that was mostly thanks to our behavioral executive. However, boss still finished with an average speed of 15 miles per hour in just over 4 hours, and was almost 20 minutes ahead of the second place team. So, you know, we were pretty happy with its performance. Now, there are a few key lessons that we took away from all this, apart from realizing just how many months you can live without sleep and a social life. And the first one, in terms of planning, was that using an accurate vehicle model really enabled us to push the limits of acceleration and speed, because we were confident that boss could do what we were asking him to do. So it was this reason that I believe was one of the major advantages that we had for why boss was so fast and, you know, so confident in its execution, while some of the other vehicles were fairly timid. Now, secondly, exploiting prior planning can be hugely useful, far more useful than I realized before starting this project. Now, as I mentioned, we use this in several places, from lookup tables for our trajectory generator to lookup tables for our lattice planner, our heuristics, also the pre-planning and the multiple planners running online. All of this information basically allowed us to cheat and get better solutions than we should have gotten in the time that we actually had for planning. And finally, although simplicity was central to our high-level system development, and we put a lot of effort into trying to make sure that the interface between our various systems and modules was as clean and simple as possible, when it came to planning, although very simple approximate planners can work very well 95% of the time, power and generality and completeness are priceless when you need them. And you know that if you take the option of making a simple planner, then the one scenario that you know would fail is going to be presented to you on the final race day. So using a very high fidelity, high dimensional lattice planner proves sort of time and time again to be the right choice for us. And then that's it. Thanks very much. This is just a final view of boss, seeing everyone cheering him on as he comes into the finish line. And I think in the other video that we had from the crowd, you can hear people yelling, "Get out of the way," to Junior. But boss was a little bit more cordial himself, so he just comes in and there's Tony Taylor. And that's it. Thanks very much. Hans.
So,
excuse me.
I'm not sure why you're generating sets of trajectories, given you already have the capability of refining them and in some sense, you could be optimizing a single trajectory to do exactly what you want, rather than selecting from a set.
So we, in our trajectory optimization step, we're not taking into account any of the obstacles. Now, we could be doing that, but for us, it turned out to be more efficient, and I know that Tom has used the trajectory generator to do exactly that. But it tends to be more expensive to try to do that than to generate a whole bunch and then select between them which one is collision-free and still gets you roughly where you want to go. I mean, the other answer to that is that we don't know necessarily exactly that we want to get to one specific point on the path, right? So we may, if we were to use that approach, we would select a point on the path and say, I'm going to do my darndest to get there and generate a trajectory, but in doing so, we may end up doing stuff that is sort of suboptimal when we don't really care. So in lane driving, we don't care exactly about being in the middle of the road if it's going to cost us more in terms of
Right, but you
maneuvering.
do have to have something that drives the selection, and that
Right.
same thing could drive optimization.
That's true. Particularly if we allowed the endpoint to be free,
Right.
then yeah. And that's what we're trying to approximate cheaply, is that result. Yeah, JP.
You talk about predicting the motion of oncoming vehicles as you plan your path. And when you're doing that, to a great extent, you have to trust that the other vehicle is going to stay on its lane. So there's always a chance that it's going to veer onto your lane.
Yep.
How do you handle that?
We cross our fingers. So if you're driving in the sort of lanes, I mean, we were dealing with at times 9 or 10 foot wide lanes, and if you're driving down a lane at 30 miles per hour, and this is something that we do as people all the time, if you're driving at 30 miles per hour down one lane and there's a car coming towards you at 30 miles per hour, they can kill you if they want to. There is nothing that you can do to get out of their way. So we do this fairly intelligent multi-hypothesis prediction. That's not something that planning did. That was some of the wizardry of our perception team that worked really well. And so we use that as a better approximation than just where they currently are. But yeah, there is definitely some sort of hope that they're not going to try to jump into our lane. Now, part of the way that we sort of mitigate that risk is that we're trying not to hug the left side of our lane as well, right? So we're trying to stay away from the side of the lane to give that a little bit of buffer. But yeah, if Oshkosh wanted to take us out, they could take us out. And that, I mean, that's scary, right? In a competition like this that you put that much effort into. But Boris.
In your parking lot planner, how did you have your cost function take into account the trade-off between curvature and distance travel, especially since you also have velocity to consider because that trade-off would change as a function?
So we played around with a lot of things, looking at curvature and biasing the cost based on that. It turned out what worked best for us was pure distance of the action. It seems surprising, but so our cost function in our Lattice Planner is purely distance-based.
So you would go to the extreme of what the turning radius could be? And then
Yeah, so we didn't actually allow actions that went all the way to the extreme. Because it was discontinuous in curvature, we would sort of throttle it so that we had a little bit more wiggle room to actually track them. But we would allow it. The big cost, so we had distance was the major cost calculation, but then when there was a velocity switching point, the reason we chose velocity instead of curvature as our fourth dimension was because it's really expensive in terms of time to stop when you've been moving 15 miles per hour and then change gears and then reverse and likewise change from reverse to drive. So we wanted to be able to reason about that time cost. And so that's why we had these, the velocity as the extra dimension. So our velocity dimension only had two values, sort of positive full speed, negative full speed. Yeah.
How sensitive is the planning to either the weight of the vehicle or even like damage?
So the weight it wasn't very sensitive to. I mean, we didn't tune our vehicle model to the point where we had to know which people were developing in the vehicle at the time. A flat tire, depending if it actually knocked the alignment out, it would cause trouble. So we also contemplated trying to use an adaptive vehicle model whereby online we could be updating it so that if we hit a curb really hard and our alignment got off, we could actually update our vehicle model so that we could still correctly continue. But we decided that was one of these sort of very low, sort of low on the stack of all of the things that we had to do in a very short time, so we didn't do that. So if the alignment was off, we would have sort of a constant offset, and it would affect us.
And that would require you to update it rather than me to tackle the problem itself?
In our system, yes. So I mean, it's quite possible to have an adaptive approach, but then again, there are also a lot of scary factors about doing that as well. You know, you have the vehicle drive and suddenly it's updating its model and perhaps there's a bug in that update and then it's driving off the road when it actually has nothing problem. So, you know, it was definitely something we thought about, and in the end we decided against it. We also had run flat tires and other things to mitigate that risk as well. Chris?
So the planning system was awesome, but it was 3 of these really magically powerful Intel cores, right? What if I were to tell you you had
2, right? 2. Did you have a third one that I didn't know about?
There was 2 for 3D Planner, and then there was another one for the local planner, right?
Okay, 3 cores. Yeah.
Okay, let's say you had 1 or half of them. How would you change them?
So I'd get rid of the multiple planners icing on the cake. If I had to make a call where I had to actually change the 3D planner because we didn't have enough processing for it, I think I would start by reducing the resolution of the lattice. So we're already using this multi-resolution lattice. We can reduce the action space, reduce the discretization of the heading potentially. I think that the general approach that we took was a good one. I think that using this higher fidelity lattice planner is kind of the right solution. I think we can make it arbitrarily more efficient by increasing the weight on our heuristics so that we're getting more and more suboptimal solutions, by making it denser. And in the limit, we're going to approach something that's similar to a 2D planner. But I think having that framework there is definitely something that's useful. I think for the local planner, we're generating this set of trajectories. We can generate fewer. We can do fewer optimization steps on each one. I think there are definitely knobs that we can turn pretty easily for that component.
I guess the other point is that magical processors are cheaper than magical days.
Magical what, say?
Magical processors are cheaper than magical days.
Oh, thanks, Tuck. Matt.
See, the multi-resolution thing is interesting. You have 2 different resolutions there, and you have a kind of fixed strategy about when you're going to use them. I wonder if you've thought about something that's maybe that pushes the idea further than that.
Yeah, our next paper.
Would be valuable.
Yeah, no, absolutely. I mean, so right now, yeah, what we have is kind of a hack. It's a fairly well-founded hack, but it's still kind of a hack, right? We have this distance that we're going to allow it to be high resolution. What would be smarter, and Max and I have talked about this, and maybe we'll do something about it, would be that you're planning in sort of a low-resolution space all the time. And when you start coming into trouble in that low-resolution space, you can realize that you're getting stuck in minima. And then you can adaptively increase the resolution where it's needed during the search. That's something that, on the face of it, is not difficult to do. What we would like to do is be able to do that in a way that's sort of theoretically well-founded, so that we can still prove bounds on the quality of the solution that we get. Not just bounds in terms of, okay, it's going to be at least as good as what you get from the low resolution. We want to do sort of something better than that, because the real power would be when you start with an extremely low resolution planner, and then you can adapt it to become much higher resolution, and interleaving that would be really, really cool, I think. But a great idea, and one that I'd like to look at. Ross?
So what would you say is the biggest challenge in this whole planning picture? You have to spend a lot of time thinking parameters.
So the most annoying thing that we had to do was the cost function for the local planner. All right. Now I've talked to several people since and during, and we're like, oh, you should learn the cost function for the parameter, and that's fine. But the most annoying bit was not actually coming up with the magic numbers. It was coming up with the magic features. So we would run the planner, and we would say, okay, we want to stay away from obstacles, rah, throw in some numbers. The numbers all seem to work pretty well. We know that obstacles are bad, center of the road is good. And that, you know, that was okay. But what would happen is that we'd run it and then we'd see it do something silly, like it would sort of swerve towards a pole when a car was coming or something, and then we'd be like, oh, okay, we need to add in sort of non-linear costs for, well, it's okay to go out of the lane a little bit, but we really don't want you going out too much, and we don't want you going on the curb, but if you're going fast, we don't want you sort of swerving away from the curb. And so it was figuring out which features should be incorporated into this cost function was a real pain. So sort of automated feature extraction from human-driven data would be great. That would be really cool. In terms of the most challenging in terms of how much time we spent on it, or the most challenging, interesting problem, or all of the above. I think the most interesting problem was this parking lot planning, right? So I think, you know, I haven't seen what all of the other teams did in their systems, but Max and I really sort of loved the idea of trying to develop a system that could really handle the hardest case. So in that sense, we were kind of biased to try to go a little bit overboard so that we would not end the challenge saying, man, I wish we had added that dimension, or man, I wish our planner had been able to do that. So that was definitely, for me, the most interesting problem, was figuring out how can we plan over these huge distances, and instead of doing this, you know, sort of local and global planning, like field Dstar stuff, you know, how can we try to do all global over the sort of distances that we used to have to do these very approximate planning algorithms, and how can we do that fast enough that we can steal Stanford's parking spot, right? That was kind of the goal. Chris?
But that's very counterintuitive. A big parking lot is in some sense the easiest place to drive. It's empty.
Right.
And you know that the size of your maneuvers has a limited radius. So the globality beyond that radius is sort of wasted.
So I agree that big parking lots are easy to drive through if they're clear, but you know, you saw the simulation environment that we had. Like, if they're not clear, they can be extremely difficult to drive through, right? So imagine you have a maze in a parking lot, and you've got to keep in mind that the Tahoe that we're dealing with is a big I mean, this was not a Mini Cooper that we were trying to navigate into parking spots. So reasoning about those constraints in the planner rather than using some sort of 2D, you know, optimistic C-space map, or pessimistic. Pessimistic would block off, you know, a lot of roads would be completely blocked off by pessimistic C-space. So using an optimistic C-space could really get us into situations that we couldn't maneuver out of. So exactly for the reason that you say, you know, I agree completely. You have this limited area over which you can perform maneuvers, but in order to track fairly wide, I mean, you'd probably be surprised, but fairly wide roads are difficult to fit through with the Tahoe. You know, when we were tuning some of our on-road stuff, we were like, oh, the back wheels are going out of the lane, and then we're like, okay, we'll change that. Now the front wheels are going out of the lane. And it turns out that we've got this bus that you try to put around these tight lanes, and some part of it's going to have to stick out. So if we're not reasoning about the actual vehicle constraints and we're using some approximation, either pessimistic or optimistic, then we're going to get in places where, you know, we're really going to get stuck, and then we're going to look stupid, and we don't want to make CMU look stupid. So yes.
Same note of looking stupid, is that why they took a lot of the cars out, you think, for the final race?
I think so. You know, when we saw the first qualifier event, so in the Urban Challenge they had this series of 3 qualification rounds, and one of them was really exciting because the vehicles left from the grandstand, they went off into this area of the course that you couldn't see, so no one had any idea what was going on back there, and then they would come back or not. So the first time all the vehicles went, 4 out of 35 came back when the first time that they went on this round. And so then that was the video that I showed of us parking between the cars. And, you know, we saw, when afterwards we were watching that video and we thought, you know, this is great. DARPA has really brung it, right? You know, they've got cars here, they've got obstacles, they had cars blocking the road, they had barrels in the middle of the road. It was perfect. Max and I were sort of salivating at this footage. And I think what DARPA decided was, yeah, this is great. 4 cars made it through this course, right? If 4 cars make it through this course and then we put all this sort of stuff in the final and they have to drive for 6 hours, what are the chances that someone's going to win? So I think, you know, DARPA did what they thought was the best approach to guarantee that someone would win. I think, you know, obviously we would have really liked it to be very hard so that you could sort of see, you know, the true capabilities of the vehicles. But yeah, I think the reason
that came back, were they at the top four?
the four that came back.
I'm just curious if those were that ended up being the four anyway.
Yes, I think they were the top four.
Virginia Tech didn't come back the first time, I think.
So who was the fourth then? It was us, MIT, Stanford. I was pretty sure it was us, MIT, Stanford, and Virginia Tech that came back from the course P.
Yeah, I don't think MIT did. I think they got stuck up at the first.
Go back and look at my hours of tape.
Yeah, we'll have to figure it out. You think it was Carola that came back with us?
I remember them coming back.
Sounds right.
Yeah. Almost then, almost the same teams. But. Ross.
So you mentioned cost conscious. So I was wondering, if you had to do it again, would you do it more on a
Yes. You don't need to continue. Yes, I would definitely learn it. I mean, if I had to do it again, I think if I had to do it again, the way that I would do it is come up with every possible feature that I thought could potentially be useful, even those that I thought were unlikely, and I would probably throw it into a big learner. Test the heck out of it, but I mean, we tested the heck out of everything, right? So throwing that into a learner on day one and then spending your time really testing it, I think would do a good job, and it would save me many tears and heartaches of trying to throw these features in myself. Anything else?
I have something to say. This is all going to be on the Discovery Channel in about 2 months. I finally got the final word. They are making it's either 2 or 3 hour program that will either run as one program or as 2 separate programs. But either way, look for it on Discovery Channel.
Great. Now, I remember when Discovery guys came, we had some fantastic footage of us in the vehicle when we were really trying to optimize the speed around corners, and we took a couple very hot. I think, you know, it'll be interesting to see what's on that video. All right, thank you very much.